for the next session of ICFP. And to start us off, we have Guillaume Boisseau, who will tell us everything that we need to know about the Yoneda Lemma.
Thank you very much. Good afternoon, everyone. It's a great honor to be here. Today, I want to give some credit where credit is due. We all know theorems, and theorems are great, but they get all the credit where most of the work is done by lemmas. So today I'm going to talk about a very famous lemma called the Yoneda Lemma, and I'm going to present it and use it to rediscover the infamous Profunctor optics that some of us may have heard about. This is joint work with my supervisor, Jeremy. So the Yoneda Lemma is a lot about a specific perspective that says that a lot can be understood about an object from its relationships. So I've got a bunch of examples that come from math. You don't need to be familiar with all the examples, but I'll go through them. So the simple example is, well, if I look at the set X, and I look at functions from the singleton set to X, there's one such function per element in X. So if I look at all the functions, the set of all functions from the singleton to X, well, I get exactly all the elements of X. So I've got something that gives me all the information I need about X. I have X itself. If I look at continuous functions, that has a bit more structure. Here, X is a measurable space, or something that understands continuous functions, for example, the real line. And if I look at continuous functions from the singleton space to X, well, again, that gives me all the elements of X, but I still don't have, I only have the elements. I may be interested in a bit more structure. So I could probe X with other things, look at maps from, for example, the circle to X. If you know what it is, it's the loop space of X. And there's a particular space called the Sierpinski space, and any map from X to S gives me the open sets of X. And it turns out that from this last info and the first one, I can reconstruct X itself. That's quite interesting. With just the set of maps relating to X, I can reconstruct the entirety of X. Another example from group theory, if you're more familiar with that, or if you're not, it's fine, or the group homomorphisms between the singleton group and a particular group X are not very interesting. There's only one such. It's not good. But if I look from the group of integers to X, again, I have enough information to reconstruct X itself. So all of those examples have something in common, is that we look at a particular object through the maps that go either into it or from it, and that preserve the structure in some way. Now the question is, well, what if I probed from all other objects? So I need to make this notion a bit clear. What objects are we talking about? What is this probing exactly? So this is made clear by category theory. So a category is simply a collection of things that can be composed. So good examples include, well, functions, continuous functions, group homomorphisms, if you know those, Haskell functions, they can be composed as we all know. Elements of a monoid also apply to that. In general, those things have types. So they have a source and a target. And if I have a source and a target A and B, I will not see A, B, the sets of all maps. And now let's try to understand what I meant by probing from all objects earlier. So if I've got a particular object of interest A, and I look at all the maps from A to some X, the X will be generic. And if I take this set, and then I collect it into some f of X. We don't really know what f is, we don't really care. The idea is that I collect those maps, and then I collect them into something. And I do this for all X's. What the Yoneda Lemma tells us is that this is enough to have all the info about f of A. So stare at it for a bit. What this says is that uniquely from information about maps from A to something, I can get all the structure I want about A. So f here can vary, can be multiple things that can give me information about the structure of A, but in general, that's enough to reconstruct A itself. So I'll illustrate a bit what this lemma does in Haskell. So I'm assuming most of you are familiar with the notation. So if this is exactly the same thing written in Haskell notation, so maps from A to X are functions A arrow X in Haskell, and here, when f is a functor, this equality holds. And some examples. include, if you look at the type of the identity function, that's the ticket thing on the left, it's for all x, x arrow x. Well, we know that for any type x, the type is isomorphic to the functions from the unit into x. Any function from unit into x is simply a choice of a particular element of that type. So I get this alternative, this equivalent type for the identity function. And then by the Yoneda lemma, where f here is chosen to be the identity, I get that this is isomorphic to the singleton, to the, sorry, the unit type. What does that mean? Well, the unit type is the type that has exactly one inhabitant. So that means that the type on the left, the type of the identity function, has exactly one inhabitant. And we know it is the identity function. But what this says is that there's nothing else of that type. We can expand to a slightly more complicated example where I've got maps from pairs of x to x. Intuitively, a map from a pair of x to x, it's either the left projection, I take the left element of the pair, or the right projection, where I take the right element of the pair. And using the Yoneda lemma again, it turns out that this is exactly true. So this is isomorphic to bool, which is the type with exactly two elements. So I've got exactly two functions of that type. For a bit slightly more intricate example is if you know about monads and you look at the type of bind. So to define a monad, those who don't know, you can do that for a second. To define a monad, you define two maps, the second of which has this big type over there. And if I manipulate this type a bit, using the Yoneda lemma, it turns out it's equal to the second type. But those of you who know about monads will recognize that the first is the type of bind, and the second is the type of join. There are generally two presentations of monads. The ones that are more Haskell-oriented tend to define monads using a return function and a bind function. So that's the bind is a type on the top. But those more categorically inclined tend to define them using a return map and a join map. And it is known, it's folklore, and easy to prove that those two definitions are equivalent. Well, here's a short proof on 2 lines that those are two presentations of monads that define the exact same data. So what I'll be interested in today will not be the Yoneda lemma itself, but some corollary of it. And in particular, there's a corollary called the Yoneda embedding. In the particular case where I choose f of x to be mapped from b to x, I've got this kind of symmetrical formula here that tells me that if I can transform a probe into a probe from A into a probe from B, then that's exactly equivalent to having a map from B to A. You can see the isomorphism work. From left to right, it's pre-composition, and from right to left is applying to identity. And this embedding will be useful in a second. But a more powerful, equivalently powerful, but more interesting corollary is the following. If from this Yoneda embedding, I can derive what can be called indirect equality, which says that A is isomorphic to B. And that's in a structure-preserving sense, because we're in a general setting of category theory. So A is isomorphic to B if and only if, for every x, probes from A are isomorphic to probes from B. And that's quite powerful, because then I can go back to the motto I had earlier. A lot can be understood about an object from its relationship, and change it. Everything can be understood about an object from its relationships. And this is exactly what this formula says. So this is basically an overview of the Yoneda lemma and the underlying philosophy of it, if you wish. And in what follows, I will introduce a slightly different corollary of the Yoneda lemma and then use it to derive the infamous Profunctor optics. So we need to go deeper. We know we've been with the Yoneda embedding, been from A to B to a map from something of A to something of B. And this thing from probes of B to probes of A, that looks like some sort of map. I can compose those for sure. I can go from B to A and A to X and to Z, and I can compose those. Well, they make a category. It's called the functor category. That's denoted bracket C sets. And this functor category, well, we can see that this map here is simply exactly a map between those two probe functors, if we could call those. And since we have, again, a map in a category, we can apply the Yoneda embedding a second time to go deeper, and we get this quite disgusting looking formula. Don't stare at it too long, but maybe stare at it long enough to notice that, I can't point unfortunately, but notice that the right-hand side of the arrow, for example, has the shape of the Yoneda lemma. It's interesting how we find lots of Yonedas happening at the same time in these few lines. But if I apply the Yoneda lemma, I've got this interesting formula. So let's forget about the derivation and look just at the formula here. I've put it in the center. Let's look at what it says. If I write it in Haskell notation, for clarity for people who are more familiar with that notation, it says that having a map from A to B is exactly the same as having a map that works for every functor f, and that goes from f of A to f of B. The isomorphism can be made clear if you go from left to right. It's the well-known fmap function that for any functor f, transform a map from A to B, transform it into a map into the functor from fa to fb. And then to go from right to left, well, it works for any functor. So in particular for the identity functor, that is the identity just does nothing, well, if I apply the identity functor to the right-hand side, I get exactly a map A to B. And what's interesting is that this is a proper isomorphism. Those are the same thing. So for now, let's just leave it at that. Let's remember what we dubbed the double Yoneda embedding for obvious reasons. And let's talk a bit about optics. So this is the first talk of the session about bidirectional programming, so you will hear about lenses, but let me still introduce a bit those things. And let me start with adapters. So adapters are an interesting solution to a code and software engineering problem, which is code reuse. And the idea is if I've got two types, A and B, that are somewhat isomorphic. For example, if I have points in Cartesian coordinates and points in polar coordinates, I want to convert from one to the other and back. And I may want to do that quite often, so the idea of adapters is to package those two directions, those two transformations, into one thing. And then from there, I can define a number of generic combinators that will use adapters and do manipulations. So for example, modify A for adapter, takes an adapter and a map that modifies A's and transform it into a map that modifies B's. Since A's and B's are, intuitively, they are the same, it's logical that we can do that. What's interesting is that adapters can be composed. If I go from A to B and back, and B to C and back, I can go from A to C and back. So they form a category, and this is where we will go back to the Yoneda lemma in a second. But what we do with those is we can easily string them together and then apply some combinators, and then in a very sort of generic way over those sort of pairs of identical types, we can define functions and modify data. That's quite useful. There's libraries that use those things. But they tend to not only use the very simple adapters, but they use more intricate things, including, for example, lenses. And again, you will hear more about those, but here is a simple introduction. A lens from A to B is intuitively something that says that A is a part of B. That is that B is an A and something else. So I've got two functions, something that retrieves the A from the B, and something that puts back a new A into a B and returns a new B. And again, I can define a bunch of combinators on those, like modify also is definable on lenses, interestingly enough. And I can compose lenses as well. It's a bit less obvious, but I still can, and from that, I get very interesting combinators. Now, from staring at this, you may notice that they look quite the same, and in particular, it looks like every adapter is a lens, and intuitively it works out, because if A and B are the same thing, then B is exactly an A plus, nothing else, but nothing else is something else. So every adapter is a lens, and if I use those in a program, I may want to have adapters and lenses together working to construct a program. But I'd like to tell somehow my language that, well, every adapter is a lens. I don't want to explicitly transform from one to the other. I'd like to be able to automatically transform adapter into a lens. And if I have other things that are similar, I'd like to transform automatically from one to the other. And this is where the double Yoneda embedding comes. So if I stare again at the formula over there, let me define adaptors. Notice there's an O here. Adaptors being those functors from adapter to set. Let's not delve into what the details of that are, but the lemma tells me that adapters from A to B are isomorphic to this polymorphic formula here. Why not? Let's do the same for lenses. How is that interesting? Well, to tell Haskell what adaptors and lensors are, we need to define type classes. So we define them like this, but we can be a bit more clever because we know that every adapter is a lens. Therefore, every lensor is an adaptor because they're function from, so they're contravariant. So I can tell Haskell, well, actually all lensors, I know there will be adapters, so I can add this requirement here. The arrow here, that's Haskell notation. It's slightly backward from intuition, but that says that any lensor must be an adapter. What do we get? Well, since an adapter in that polymorphic definition, since an adapter from this in that polymorphic definition works for any adapter F, it works for any lensor. So an adapter can be used where a lens needs to be. So I've got automatic lifting. Anything of type adapter over there fits in a hole that needs a lens. And I solve my software engineering problem over there. I just have this interesting packaging of things, and then I can use one in place of the other where it makes sense, but not where it doesn't. And the other thing we get, and that's very interesting, we get composition for free. Because as you can see, the things on the right-hand side of the isomorphisms are arrows, polymorphic arrows, but kind of normal Haskell arrows we're used to having for all quantifications. That's fine. If I could go from FA to FB and from FB to FC, it's quite evident how in Haskell I would simply I would compose those and go from FA to FC. So I get composition for free in that setting, and the double Yoneda embedding tells us that this composition is actually compatible with the composition of adapters and lenses that I mentioned earlier. So we get not only every adapter automatically works if I needed to use as a lens, but I can compose those things together. And Haskell will figure out the right type for all those things. And in fact, there are quite a few, half a dozen different adapter-like, sort of lens-like things that can be composed together, lift automatically to the appropriate level, and make a very interesting family of combinators to define very powerful data transformations. So this is here Profunctor optics, and this is what the Yoneda Lemma tells you. Thank you very much.
So we have one question at least. So during the talk, you started off by saying that almost everything follows from an object, and it's by just studying the relation with its neighbors.
Yep.
And then you kind of corrected that halfway through the talk and said, well, actually everything follows from its relation with its neighbors.
Yep.
But there was a question, as you started, I could see it come in, which said, well, what would be examples that don't follow from just studying a neighbor?
Well, what actually follows is equality up to isomorphism. So an isomorphism is a good way of saying those things have the same structure up to some structure I'm interested in. So indeed, if I look at, I don't know, groups, I can say they have the same group structure, but if I actually looked at whether the element 0 actually belongs to one or the other, that's not really a thing that an isomorphism preserves. So indeed, we only get well-behaved structure equality, which some people say is the only thing you ever want if you want to, not be evil. But agreed, it doesn't apply for everything.
Okay, fair enough. So one thing that you've done is you've gone from a very simple data representation of adapters and lenses and shifted to a functional one, right? Where
Yep.
you have introduced polymorphism and ad hoc class constraints. Do you have any experience with if the added complication creates worse type errors? That's another question.
I mean, yes, and it's not great. So it's not great if you do it naively. Interesting enough, there's some libraries that have done that quite cleverly in Haskell, because Haskell has some devices to help you have custom type errors. So there are some ways to make type errors slightly less intricate, but indeed, in general, this is makes it very hard to understand for someone who doesn't know the underlying thing, including.
And there's another question, which is just what is a profunctor?
I was expecting that question to some extent, and I've got a slide for that, kind of. The idea is simply that the adapters I've mentioned are almost profunctors. It's just I'm working in a slightly simpler setting than complete profunctor optics, because I use functors that have 1 parameters, and profunctors are almost the same with 2 parameters. So if you look at the paper, you'll have a whole definition of the same things in a context where things have 2 parameters, and in that context, the adapters are exactly profunctors, and the lensors are exactly strong profunctors. And there's a bunch of other of those things. So it's just a slightly generalized setting, and you can read the paper. It's full of neat proofs.
Okay, so one final question. So the Yoneda Lemma is incredibly useful and it's powerful, but sometimes I find myself, I'm doing a proof, and at what point should I really be thinking in my head and think, I should be using the Yoneda Lemma here, because that would make my life easier?
That's a very good question. I don't know. I think it comes from practice of doing a lot of Yoneda Lemmas, and then you start seeing them everywhere, but I don't really know. There is, however, a interesting pattern to all the applications of the Yoneda Lemma, is that, well, they define an isomorphism, for starters, and usually one direction of the isomorphism uses applying something to the identity. So if we look at the Yoneda Lemma up there, if I take the right-hand side, and I pick x equal a, then I can apply the identity to that thing. And that gives me an f of a. And that's the thing on the left. So to go from left to right, I apply to the identity, and from right to left, no, sorry, backwards. To go from right to left, I apply the identity, and from left to right, I use the functorial mapping. And that's a very general pattern that happens everywhere. So if you happen to detect that you're using fmap in the direction, apply identity in the other, you probably have an instance of Yoneda.
All right, thank you very much. Let's thank Guillaume again.